Welcome to the Week 9 review for Math 2413. In this one, we'll be talking about differentials again, since I didn't quite cover it as well as I would have liked last week. And then we'll also go into how to find some maximums and minimums, talk about a few important theorems, so like the extreme value theorem and then the mean value theorem as well. All right, so let's get going. Again, first we're going to start off with differentials. If you'll recall from last week, differentials are a way we can approximate a function value. So if we know the value of a function at a point A, and it's really close to a point X, we can kind of use a tangent line approximation in order to find a point that is very close to the actual function value. So I've written this formula up here. And what that tells us is if we're looking for a function value at a point X, and we know our point A, well, we can approximate the value of our point X by taking the value at our point A and simply adding on our small change in Y right here. And that will give us a value that is very close to our correct value, but not quite there. But it still serves as a great approximation. And the way we get that is we simply take our function value at A and then add our slope at that point, or at that point A. Sorry, this should be an A as well. And then multiply it by the change in X. And this is the same as saying our function value at A plus a small change in Y. So for example, if we wanted to approximate, I think there's a question in chat. Oh, good call, good call. Oh, yes, the mic is on. It's definitely working on my end.
I don't know if they can hear you.
Ooh, I've done this before. Yes. Can anyone else online hear me? Because on my end it says everything's working well. All right. Good luck.
Let me see if I can hear it.
Yeah. In the meantime, I will be writing out our example problem. Let's see, other people online, can you hear me just fine or no? All right, good to make sure. Perfect. So we'll start with this example. Let's say we have a cube and we measured the side length to be 7 centimeters with an error of plus or minus 1/10 of a centimeter. We are interested in knowing the maximum error in measuring the volume of the cube. Well, in order to solve this, what we want to start by doing is writing an equation for volume. We know that the volume is equal to the side length cubed. So, if we wanted to find a change in volume, well, we would take the derivative of our volume equation. which would get us 3s squared times a small change in s. And I do write my s's cursive because otherwise they look like 5s. So just a heads up, that's what my s's look like. In this case, we now know enough to solve for our small change in volume. We simply plug in what we know. We know the side length is 7, and we know that the error is 0.1, and this would give us 1.47. Actually, sorry, 14.7, misplaced my decimal there. 14.7 centimeters cubed as our potential delta V, which is our error in measuring volume. Any questions? Okay. In that case, let's go ahead and do a couple of quick practice problems. I don't think this one was on the last review, but maybe it was. I'll give you guys a couple of minutes to work on those. one?
No, I was still thinking about the first one because I kind of confused myself. Let's- So the differential formula is the change in y is equal to the derivative of your formula times the change in x. The derivative of 2.99 squared is just 0.
Right, so maybe you want the function to give you a good approximation of 2.99 squared. That's kind of where we want to start out at. Part B, I think you are a little bit off. Make sure we're approximating the volume and not just the change in volume. Let's talk a little bit about part A, since it seems like a few of you guys are struggling with this one. With a lot of these differentials problems, what we want to start by doing is writing a function that we can then use to represent our situation. So in this case, we're trying to approximate 2.99 squared. Well, 2.99 is approximately equal to 3, so maybe 2.99 squared should be approximately equal to 3 squared. But really what we're doing in each case is we're using a general function of just squaring something else.
Oh, so x squared would be our.
Right. So
Oh,
we have a function f of x is equal to x squared. That might help you guys out some.
that helps me out a lot. I know I need something where I'm not.
So let's just go over problem part A. If you'll recall our whole, come on, OneNote, there we go. Our whole differentials formula is that we're looking for our approximation is f of a plus f prime of a times delta x, where a is the point we're approximating. Sorry, a is our approximation. So in this case, we would let a be equal to 3. And delta x is equal to x minus a. So it's equal to 2.99 minus 3. So it's equal to minus 0.01. Well, using our f of x, we can find f prime, which is simply 2x. And we need, according to our formula, f prime of a. So f prime of 3 is equal to 2 times 3, which is equal to 6. Well, then our approximation, f of x, is about equal to f of a plus f prime of a times delta x. And this is equal to, well, f of a, I can take my a value, 3, and plug it into f of x, and I get 3 squared, which is 9, plus f prime of a, 6, times delta x, which is negative 0.01. And this gets me 9 minus 0.06, which is 8.94. Does that process make sense? It is linearization. That is.
I knew that was part of like the end, but what's the point of differentials then? You just like, isn't that just semantics? Like.
Yes, I've always called it differentials. Like, I've actually, just the way that I was taught, I've pretty rarely heard it called linearization. So I just always refer to it as differentials, which is maybe just a thing on my end. But it's concepts you're familiar with, right?
Yes, sir. But the differential is just like the multiplication part of the linearization problem, is what I was taught. Or what I understood, I guess.
Okay, yeah, that's fair. Regardless, even when you're being asked to approximate it using the differential, you still use your differential, which is this part here, right? And you still approximated your right value.
So without the addition, what does that get you? What's your differential get you?
Without your addition, what does it get you? It gets you an approximation for how far off you will be. So it gives you this little delta y right here.
Oh.
Which is not quite the true difference, but it's a close approximation for that difference. But does this problem make sense now?
Yes, sir.
Perfect, perfect. Did you get a chance to look at part B? All right, then we will go ahead and go over that one as well. For this one, it's a little more similar to the example I gave earlier. First, we always want to write our equation. In this case, we're just using the volume of the sphere, which is 4/3 pi r cubed. And again, we know that because it's expanding by 0.2 centimeters, we can find our delta r. It's given, it is 0.2 centimeters. Well, we can find then our delta v by taking the derivative of our volume equation, and we get 4 pi r squared times delta r. Now then, we can simply plug in our values because we're given that our radius is 11. So our delta v is approximately equal to 4 pi times 11 squared times 0.2. And then we know that our new volume should be approximately equal to our old volume plus our change in volume. Right, nothing new here. Well then, our new volume is approximately equal to our old volume, so 4/3 times pi times 11 cubed plus 4 pi times 11 squared times 2. or 0.2, sorry. And what this comes out to be is it comes out to be, after rounding, 5879.36 centimeters cubed. So that's our approximation. If you're interested, the actual volume where you just calculate using 4/3 pi times 11.2 cubed. This actual volume is 5884.949 centimeters cubed. So you can see our approximation was maybe 5-ish cubic centimeters off, which is not very much considering how large our numbers are. Any questions on this problem? All right. Any questions from anyone online? Okay. All right then. In that case, we're going to move on from differentials to maxes and mins, which are one of the greatest or most common applications of calculus. Here we go. And so the key thing to remember here is what your derivative means. So if you will recall, your derivative is basically your slope. So this is a really huge concept. It's really helpful to just think of your derivative as slope because it makes a lot of things a lot more intuitive. So let's say I were to draw out a function. And that function looks something like this. I don't like that function. We're going to draw out a function that looks similar but is slightly prettier. I drew the same thing. I swear I will never become an artist. It's good enough. Okay. Well, if we look at all the points where we have a local maximum or a local minimum, then, I'm sorry, give me one more go at this. Okay, we'll do that. And I'm just going to turn that into an arrow pointing down. Perfect. If we look at all the points where we have a local maximum or a minimum, they all have something in common. And that something is they all have a horizontal tangent line. So you can see, right there you got a horizontal tangent, right there you got a horizontal tangent, and right there we have a horizontal tangent. Now, horizontal tangent means that our slope is equal to 0. But since our slope is the same thing as our derivative, that tells us that our derivative should be equal to 0. And this is true wherever we have a maximum or a minimum for a continuous function. Your derivative will be equal to 0. One thing to note, though, is it's not necessarily true that every point where you have a 0 slope is a maximum or a minimum. For example, we have this point right here, or if I can draw a decent tangent line, you can see that we do have a tangent line, but it's not a maximum or a minimum. Anyway, though, this concept is basically how we will find maximums and minimums of various functions. So, one quick definition. We call something a critical point if it is a point where your derivative is 0 or undefined. Okay, so now let's take a quick example of how we might want to find some maximums and minimums. Let's say we have a function f of x, and it is equal to 1/3 x cubed plus 4x squared plus 12x minus 6. Well then, we know that all of our maximums and minimums should occur where we have a zero slope, or where our derivative is equal to 0. So we can find our derivative. It's going to be x squared plus 8x plus 12, and set that equal to 0. In this case, I'm going to go ahead and factor my x squared plus 8x plus 12 to get x plus 6 times x plus 2 equal to 0. And then I can really easily see that the two x values I'm looking for are x equal to minus 6 and x equal to minus 2. So these are the points where I can potentially have a maximum or a minimum. Now I simply need a way to figure out whether it's a maximum or a minimum. One method that I like to use is just make a little number line and say, well, before negative 6, if I plug in, let's say, negative 10, well, then the x plus 6 term would be negative 4 times the x plus 2 term would give negative 8. That's a negative times a negative. It will give me a positive number. When I plug in a value between negative 6 and negative 2, my x plus 6 term is going to be positive. My x plus 2 term will be negative. That'll give me a negative value. Finally, plugging in a value larger than negative 2, I'll get a positive number. Now, if I just sketched out a rough idea of what the slopes would look like, I would have a positive slope leading up to negative 6, a negative slope heading away from it, and then a positive slope going away from negative 2. So you can kind of see that right here, we make a mountain, so that's going to be a maximum. And at negative 2, we make a valley, so that's going to be a minimum. So that is where our maximums and minimums occur. You could find the y values if you wanted, if a problem, for example, asked specifically for the points that are the maximums or the minimums. Points implies you would need a coordinate pair. In this case, though, I'm just looking for x values. If we wanted to find the y values, all we would do is we would take this x value and plug it into our original x equation. Okay. All right. Any questions on this example? Are relative extrema the same as local? Yes. So a local min is the same as a relative minimum. It really just means relative and local are just not necessarily absolute. Okay. In that case, let's go ahead and do a couple of practice problems. Well, actually, we'll just do one practice problem, and then we'll introduce the extreme value theorem. And I'll give you a couple of minutes to work on this. all good. Okay, let's go ahead and go over this one. Again, it's pretty straightforward, just like the example. In order to find our maximums and minimums, we're going to be looking for our critical points, which are where our derivative is equal to 0. So firstly, we need to find our derivative. I'm going to go ahead and factor out a 3. And then I can factor this more easily. So that'll give me 3 times x plus 3 times x minus 1. And I know this should be equal to 0. And now because it's factored, I can really easily see that the x values I'm looking for are -3 and +1. Again, I'm just going to make my number line. So I'd have -3 here and +1 here. When I plug in a number smaller than -3, I'm going to get a negative times a negative, so it'll give me a positive. Between -3 and +1, such as 0, I would get, well, a positive times a negative gives me a negative, and finally, above 1, I would get a positive number. So again, I can see that here we have a max, and here we have a min. If you wanted to find the actual values, we could, of course, plug in these x values. So f of -3 should give us 3 times 9 plus 6 times negative. Oh, oops, that's my derivative. Should give me -3 cubed is -27, plus 3 times -3 squared is +27, minus 9 times -3, minus 6, -9 times -3 is +27, minus 6 is +21, since these was cancelled. And also I can find f of +1, and that will give me 1 plus 3 minus 9 minus 6, which is equal to -11. So my maximum occurs at -3, 21, and my minimum occurs at 1, -11. And these are not necessarily absolute maximums or absolute minimums. These are simply local maximums and local minimums. In fact, if we were going to graph our function, it's a cubic, so it would look roughly like, well, we know we've got -3, 21 up here and 1, -11 down here. So it would look approximately like this. Because it's a cubic, we know it'll approach either positive infinity or negative infinity on the right and on the left. So this is approximately what our function looks like. You can see here we have a local max, but it's clearly beat out by any point over on this side. But what we're looking for specifically is this is the highest point in that general region. So this is why we call it a local maximum. We would say that this function doesn't have a true absolute maximum or an absolute minimum. Again, because if we picked any absolute maximum or absolute minimum, we could always find a point larger than it or smaller than it.
How did you tell that did your graphing with the plus and minus for the slope, was that of the original function, or was that of the derivative?
So this part right here?
Yes, sir.
So I am looking just at the derivative. What I'm trying to do is just get an intuitive idea of whether the slope is increasing or decreasing. So before -3, I just plugged in some value less than -3, say -5. It doesn't really have to be anything specific. Really, all I care about is whether my function is increasing or decreasing. So when I plug in something smaller than -3, here I would get a negative times a negative, which would give me a positive. Because I have a positive derivative, I know that my slope is positive or my function is increasing up until that point. And likewise, it's decreasing after that point. So if my function is increasing going into a point and decreasing afterwards, I know I must have a maximum. If they ask you to find the maximums and minimums with no specific instructions, it is safer to go with the complete coordinate. I didn't do it in the first example because I threw in a 1/3 at the beginning and I didn't want to deal with fractions. But really, the complete coordinate you can just find after you find your x values. It's not terribly hard once you get the x values. You just plug in your x values into your function and you'll end up with y values. It's also a good way to check that you found the correct maximum and the correct minimum, because if I, for instance, said, well, I think that -3 is my minimum, well, then clearly I could take a look at what I've done here and seen, well, hey, 21 is a lot bigger than -11. So maybe -3 should be my maximum instead of my minimum. So it's just another way you can check your answer as well. Okay. Let's see. And again, it's not necessarily the case that every critical point is going to be a maximum or a minimum. For example, if we just took really quick the function f of x is equal to x cubed, well, then its derivative would be 3x squared, which has critical points at x equals 0. If we drew out a number line for this one, well, we would see that before 0, we would have a positive slope, and after 0, we would have a positive slope. So here, we don't necessarily have either a max or a minimum. We can see that we're just increasing going in, increasing coming out, and similarly, that's kind of why our cubic function looks like this. So we do have a tangent line at this point 0, but it's neither a maximum or a minimum. Make sense? All right. Moving on. Now we can talk about the extreme value here. So what the extreme value theorem says is basically if you have a continuous function on a closed interval, then it has to get to an absolute maximum and an absolute minimum on that interval. Now let me write that out in words. And we'll represent a closed interval by a comma b. That is not an x. All right, and if we were to draw this out visually, basically all it's saying is, let's say I have an interval, I can use colors, from a up to b. Well, then any function I draw in between these two intervals is going to hit a maximum point and a minimum point, as long as it's continuous. For instance, I could draw a function like this. It's going to have a maximum here, the minimum here. I could also draw a function like this, and it's going to have a maximum here, and its minimum is actually going to be this endpoint here. I could even draw a function that was just linear, going from one point to the other, and I would say, well, this also has a maximum, the first endpoint, and a minimum, the second endpoint. So even though the slope is always not equal to 0, or in other words, I have no critical points, I still attain a maximum and a minimum. And that's basically all the extreme value theorem says. Now, the important thing to note is that, or I guess the big key takeaway, is that when you're trying to find maximums and minimums on a closed interval, you need to check your endpoints. So if you were just looking for your critical numbers, your numbers where the derivative is equal to 0, you would say that this linear function has no maximums or minimums on this interval, when clearly you can point to one point and say this is the largest and this is the smallest. The reason being is you need to make sure you're checking your endpoints. So I'm going to have you guys do a practice problem. Find the absolute minimum and absolute max of the function f of x is equal to x squared plus 12 divided by x minus 2 on the interval 3, 7. I'll give you guys a few minutes to work through that. Does it have to be differentiable? No, it just has to be continuous. For example, we could draw a very spiky function. That's a good question. We could draw a very spiky function and say, well, it's not differentiable at this point here or this point here, but it still has its maximums and minimums. Good question. What if I drew a horizontal line? Well, we can still pick, so you're saying if I had something like this, if we pretend that that's horizontal and I'm good at art, we can still pick a maximum value and a minimum value if we say, like, if we describe the maximum in terms of a y value and the minimum in terms of a y value. Let's say that's 3. Well, then we still have a maximum and a minimum. It's just a question of, well, how frequently does it hit that? Because one thing we could also do is we could say, oh, that's not what I wanted. We could say, what if I hit my maximum multiple times like this? Well, this says this is still allowed. Our extreme value theorem just says that we have to have a maximum, an absolute maximum. One thing you need to make sure you're aware of is where your interval is. So I'm only looking at my function on the interval from 3 to 7. All right, let's go over this problem. So in order to find the absolute minimum and absolute maximum, we're going to need to consider the endpoints and all the critical points in that interval. So we'll start by taking our derivative. We'll start by taking our derivative, and we will use the quotient rule. So that's x minus 2 times the derivative of x squared plus 12 minus x squared plus 12 times the derivative of x minus 2, which is just 1, all over x minus 2 squared. And this will give us, after simplifying, we could distribute x times 2x gives us 2x squared, minus x squared gives just 1x squared. X times 2x gives negative 2 times 2x gives minus 4x. And then we have minus 12 all over x minus 2 squared. And this should be equal to 0. Well, I know that provided that x is not equal to 2, I won't be dividing by 0. So first off, my derivative is undefined at x equals 2. So that would be one critical point, except I only care about the interval from 3 to 7. So because 2 is not in the interval from 3 to 7, I'm just going to ignore it. So then if I multiply both sides by x minus 2 squared, I get that x squared minus 4x minus 12 is equal to 0. So then factoring, I see x minus 6 times x plus 2 is equal to 0. So then I have x is equal to minus 2, or x is equal to 6. But again, negative 2 is not on my interval, so I do not care about it. Which gives us 3 points we need to check. We need to check our critical point, x equals to 6, as well as our endpoints, x equals to 3 and x equals to 7. I'm not going to bother using a number line for this one because I'm looking for the absolute minimum and absolute maximum. I'm going to need to be plugging in my function values anyway because my endpoints might mess things up. So I get that f of 6 is equal to 6 squared, 36, plus 12 is 48, divided by 6 minus 4 divided by 4. So 48 divided by 4 is 12. Next I have f of 3. And I get 3 squared is 9, plus 12 is 21, divided by 3 minus 2 is 1, so 21 over 1 is 21. And lastly, I have f of 7, which would get me 7 squared is 49, plus 12 is 59, plus 2 is 61, divided by 7 minus 2 is 5. I'm just going to leave that as 61 over 5. And from here, I can take my absolute maximum, which is pretty easy. And similarly, I can look and see that 12 is actually my absolute minimum because I know that 12 is the same as 60 over 5, and that's smaller than 61 over 5. And I could even represent this in coordinate pair form if I wanted to. The values where f prime, where your derivative doesn't exist, also counts as a critical point. Yes, this is correct. I think I mentioned that briefly up above, but yes. Yep. Or f prime of x is undefined. That is one situation where you have a critical point. Does this example make sense to everyone?
I did something
If 2 is part of the interval, then could I not multiply both sides of the denominator to clear x? And if 2 were a part of my interval, then I would actually have a vertical asymptote at x equals to 2. So my function, because I can't divide by 0, I would have a vertical asymptote, and a vertical asymptote would actually make my function discontinuous, so I wouldn't even be able to use the absolute value theorem, or the extreme value theorem at all. So one of the conditions we need to use the extreme value theorem is continuity, and because this function is continuous on the interval, we can use it. If the interval did include positive 2, where we have a discontinuity, we couldn't use it. Does that make sense? All right.
So my kind of problem solving was I used the instead of using quotient rule, I used product rule, and so I got to the point where I got 0, 2, and then I got -5 instead of 6.
Oh. Interesting. I will take a quick look at that.
So I did this mess. So I'm going to simplify equal not my x minus 2 over 1. And I got this term and this term. And then from there I set that equal 0. And I set this equal 0, so I got a 2. So then from here I got, I was really unsure of this part right here, but I got it down to x minus 2 and x squared plus 12. So then what I did is I moved this over and I set this over here from equal to 2 because I moved that 2 over. I set this over here from equal to 2 because I moved that. So then 12 minus 2 is -10. Square root of -10 is just -5.
That's the square root of starters. What's this like? It looks like you got that square. So that's minus x minus 2 to the first.
So I'd done something else different first than I erased, so I just
Yeah. Yeah. Of course. All right. Let's talk about our last topic of the day, the mean value theorem. This one's a fun one. So the mean value theorem is pretty intuitive. Come on, OneNote. There we go. And what the mean value theorem says is that if we have a continuous function on a closed interval, so for example, we could have something like this. I don't like that one. Something like this. Well, then all that our mean value theorem says is that at some point on our interval, we're going to have a tangent line that's parallel to the average slope. In other words, our derivative has to equal our average slope at some point in this interval. I wish I could draw good tangent lines, but I can't, so sorry. If I could at least make it touch, that would be good. Good enough. Okay, so basically the mean value theorem says that at some point in a closed interval, our average slope has to equal our derivative value. And if we wanted to write that out formally, what we would say is if f is continuous on the closed interval from a to b, then we have, then there exists a c value on the open interval from a to b such that our derivative at the point c is equal to our average slope. So in this case, this would be the point c, where our derivative at that point is equal to our average slope. Note that the mean value theorem says we just have to have at least one c value. We could have more than one. We could have as many as we want. We could have infinitely many. So for example, if our function was literally just a linear function, this red line for example, well then at every point, our tangent line or our slope would just be the same as the average slope. So in this case, we could pick any point on this red line and say that's going to be our C value because it's always going to be equal to our average slope. But our mean value theorem says that we just have to have at least one. So let's go ahead and do an example. Find a C value that satisfies the mean value theorem for the function f of x is equal to x squared. We're going with a simple example on the interval from 1 to 6. Well, our mean value theorem tells us that our C value is going to be such that f prime of C, so we'll need to find our derivative. So then f prime of C is equal to 2c, and then this 2c should be equal to f of b minus f of a over b minus a, which is our average slope. Now f of b is going to be 6 squared, so 36, minus f of a is 1 squared minus 1, all over 6 minus 1. So then 2c is equal to 35 over 5. So 2c is equal to 7. So c is equal to 3 over 2. And what this tells us is that at the x value, x equals to 3 halves, we would have a slope of 7. And that's our average slope on our interval.
Why is it 3 over 2, not 7 over 2?
That is a 7 over 2. You're right. I am just I don't know why the 3 came up. I just miscopied it, but good catch. Any questions on this?
Oh wait, yes, I do have a question. So since your derivative is just your slope, right? So doesn't your secant line also have a derivative? And it's just equal to the tangent line?
So you're saying doesn't the secant line also have a derivative?
Yes.
So when you're saying the secant line, can you elaborate a bit more? Because I'm not sure.
So the red line is your secant line, correct? And
Right.
the green is your tangent. So they both have the same derivative, which is their slope. Right?
Yeah.
Okay.
So basically, what I get from that mean value theorem is that the mean value theorem base, it states that like if you have is continuous, then the secant line on f a to b is going to be
Right. So your secant line has a derivative. Its derivative is the average slope. So really the mean value theorem just says that at some point your slope has to equal the average slope.
So is your tangent line, can your tangent line change at a point?
Can your tangent line change at a point?
Yes.
Well, let's think about this. In our definition of a derivative, we know that the limit from the left should equal the limit from the right, correct?
Yes.
So if we had a different slope from the left than we did from the right, then the limit wouldn't exist, right? So could we have a tangent line? In theory, we can have a tangent line be different angles at the same point. It's just not going to be the derivative.
Yes, sir.
Does that make any sense?
Yes.
Yeah, wait, so also like, I just wanted to clarify, so mean value theorem is basically saying, yeah, the secant, the derivative of the secant of whatever like range the value that you do is going to be equal to like the derivative of the tangent line of c at the line, right? So like is Rose's theorem just basically saying that like if the derivative of f on the domain of b to like say would be 0, then f of c is going to be 0.
Rolle's theorem is specifically the instance where your average slope is 0. So with Rolle's theorem, we would have, if here's our interval, where our function starts and ends at the same value. This just says that at some point we're going to have a horizontal tangent. So Rolle's theorem is like a weaker form of the mean value theorem because it only applies specifically when you have this case where f of a is equal to f of b, or in other words, your average slope is 0. He got his name on it though because he came up with it before the mean value theorem was around, so that's why it's named after him. But yes, does the mean value theorem make sense? Perfect.
I've just now realized that they didn't tell me what a derivative was very well. At least I didn't understand.
The derivative is slope. Very, very handy way to think of it. I guess one quick example we could use for where a function has a lot of different tangent lines, but no derivative is just the absolute value function. So here we have a sharp turn. We could draw a lot of tangent lines. Someone else could probably draw a lot of tangent lines. I can draw some very poorly. We could draw a tangent line like that, like that, like that. Those are all technically tangent lines, but again, it's not differentiable at that point, so none of these are the derivative at that point because the derivative just doesn't exist. Okay. Do a couple of practice problems for the mean value theorem. I'm going to abbreviate mean value theorem MVT. I might have done that earlier. I'll give you a couple minutes to work through those.
That thing is not okay. Is the first one supposed to be really easy or like?
Oh, it's supposed to be easy. I just threw it in there to illustrate something that I'll talk about later. The second one is supposed to make you think, so.
Wait, so is the second one referring to the f of x being the first question?
Nope. Any f of x. Any f of x that is differentiable and has two real roots.
Or two real roots like Just any square root, anything.
Everybody would like is like
A root is a point where it's equal to 0.
Oh, okay, so you mean that kind of.
Yes. Part B is asking you to show that the derivative is equal to 0 at some point.
She tried to explain it. My professor tried to explain this because it's like the converse thing, right? You do like, you assume that something is true and you try to prove that it's true, and then when you can't, that's what proves the other thing is true. Is that what that is?
That's proof by contradiction, yeah.
Is that what that's the use of this? Oh,
especially the two real roots.
Not necessarily. They have to be, they don't even have to be polynomials. But if it is a polynomial, then it would have to be at least quadratic.
I assume B is also continuous.
Well, you know that it's continuous because it is differentiable, right?
Okay, so you're saying the person is saying that like f of x has two values where it's equal to 0, and then derivative of x, you're trying to prove that. That makes sense.
Right. I guess technically you could do B as a proof by contradiction. But is everyone good on part A?
I don't think so.
Have you just been looking at part B?
No, I looked at A and I got C equals 0, but
Oh,
after realizing somebody else got something different, I realized that it's something wrong.
yeah, maybe take a second look at part A real quick.
The sign of 0 is 0, right?
Right.
Same thing with 2 pi. So isn't it 0 minus 0 over, well, it doesn't matter because it's just 0.
Right, that's your average slope.
That's like, think about it in terms of unit circles. That's right.
So,
What other x value, what other value on the circle makes sine of x equals 0?
well, remember, to show that the mean value theorem holds, we would need to find a c such that f prime of c is equal to our average slope, which you said is 0. Does that make sense why we have this?
My mind just kind of boggled.
So f prime of c is our instantaneous slope, right? And we're saying that at some point, it should be equal to our average slope. So I'm asking you to find the point where your instantaneous slope is equal to your average slope.
Don't I need integrals for that to undo the derivative?
Well, this is your, you can find the derivative. You're given just your function.
Oh, so I need to take the derivative of sine x, and then it would be negative, or it'd be cosine x
And what should it be equal to?
equals 0.
And when is cosine of c equal to 0?
Get 0 to pi.
That's for sine.
Oh, wait. So it's going to be pi over 2 and 3 pi over 2.
Right. We would have pi over 2 and 3 pi over 2.
Okay, so I just didn't go far enough is what my problem was.
So my question is, do you need to provide both of these c values?
Yes. They're both within your 0 to 2 pi.
Right, but the mean value theorem only says that we're going to have at least one. So realistically, the way this question is phrased, I just said find a c that satisfies the mean value theorem. The mean value theorem just says that we're going to have at least one. So if I find one, I'm not saying that we can't have more, but I'm saying that the mean value theorem still holds. So correct answers could be c equals to pi over 2. You could also answer c equals to 3 pi over 2. And you could also answer c equals to pi over 2 and 3 pi over 2. All of these would technically be correct. Does that make sense? So that's kind of the point I'm trying to illustrate. You can have multiple points where your slope is equal to your average slope. The mean value theorem just says you're going to have at least one. Has anyone come up with an answer for part B? Let's hear it.
I was doing basically because most of it. Because the fact that you know that f of x is differentiable on the domain of all the numbers. So if it has two real roots for the base function, you know that f of some number, which is we may say f of a is equal to f of b. And then from there we can do like the whole row thing. Pretty much all three conditions are met with most of the based on the information that we got, so you can prove that there is at least one value or derivative of x. Derivative of f that equals 0.
Right. Perfect. So we are working with any general functions. So this isn't related to part A. I don't know if there was some clarification or any confusion for you people online. But the way we want to solve this is, come on, OneNote. There we go. We want to start by kind of representing our real roots. So I'm going to say that f of a is my first real root, and because it's a real root, it's going to be equal to 0. Similarly, f of b is going to be my second real root, and because it's a real root, it's also equal to 0. These are just the definitions of roots. Well then, I know that at some point on my interval between a and b, so I can say there exists a c on the open interval from a to b, such that my first derivative, f prime at c, has to be equal to my average slope on that interval. And this is by the mean value theorem. Well then, I know, because I know f of b and f of a, they're both 0. So this has to be equal to 0. Then we have that f prime of c is equal to 0. So f prime of c is a root. Or sorry, it would be c is a root of f prime of x. Since we have f prime of c is equal to 0. But does that make sense? Does the mean value theorem work on open and closed intervals? So the mean value theorem specifically says if you have a closed interval from a to b, then your c value exists on your open interval from a to b. So it works on closed intervals, but it tells you that your average slope has to occur on the open interval. Does that answer your question? All right. Any questions for part B?
I'm still kind of confused what it was asking. Like, if you're given two roots, why would you not know that it has a?
Well, it's your derivative. F prime has a real root.
Oh.
Yeah. I guess that could clarify things. Yes. So if your function has two real roots, then its derivative has to have at least one real root. Because it is differentiable everywhere, that means that any closed interval we can apply the mean value theorem on, because it's always going to be continuous on when it's differentiable.
So I guess I kind of have one other question. So how do you get like the derivative function, like or the derivative shape? How do you go from like one function to the shape of its derivative? Because that kind of seems like that they're trying to do everything to avoid that shape. But it seems like it'd be easier just to understand that.
So you're saying if you were looking at a graph, how would you sketch out its derivative?
Yes, sir.
Okay. We can do that real quick. Come on, Window.
I don't know if that's a tangent or not. If it is, don't worry about it.
Oh, it's a tangent, but that was the last question for the review anyway. So let's say we had a function and it looks like this. Well, if we wanted to sketch its derivative, all we go off of is what its slope looks like. So we start out increasing, right? Or in other words, we have a pretty positive slope, right? So we start out somewhere up here. We know we're going to hit 0 here. We're going to hit 0 here. And we're going to hit 0 here, right? And we also know that we're going to hit a point that's most negative about right here, a point that's most positive about right here, and then it's just going to get more and more negative, right? So I can kind of sketch this out. I can see that I'm becoming less and less positive as I go up here, so I should be going down. Then I hit my 0 point, and my slope becomes negative. Then my slope slowly becomes less and less negative until it becomes positive again right here. So then I'm increasing. And then once again, I hit this point where I'm no longer increasing, and I start decreasing again. Or sorry, this here would be my point where I have the maximum increase. So that's this point right here. Right here is the point where I'm no longer increasing, or in other words, my slope goes from positive to negative. And I would continue going on as like that.
So what about from like an equation? Do you just have to go through like the finding your critical points and then finding your slope kind of? So
That's usually the easiest way to do it from an equation.
okay.
A lot of the times, in fact, it's easier to take the equation, find its derivative, and then use the derivative to help you sketch the graph of your original function.
So you're saying go from your equation to a graph and then go from that graph to the graph of the derivative?
No, I'm saying go from your equation to the equation of the derivative, and then use your original equation plus the equation of the derivative to sketch the graph of your function.
Yes, sir.
So one example of that would be if I looked back at a couple of the examples I gave here, you could see if I wanted to graph my original function, x cubed plus 3x squared minus 9x minus 6, well, I can always start by graphing my y-intercept, right? -6. But I can also identify the exact x coordinates where I have maximums and minimums using my derivative. So here I can say, clearly I'm going to have a maximum at x equals -3, so I'm going to sketch that there. I'm also going to have a minimum at x equals to +1. So I'm going to put a minimum there. And then I know the general shape of a cubic, so I just have to sketch that in. And that's a lot easier than trying to just guess based on what I know about cubics to try and figure out where the maximums and minimums of a cubic would occur before actually finding the derivative. So it's actually a lot easier to work with the equations rather than just the graphs. The graphs are good for getting a general idea of something, but if you want any kind of precision, it's usually easier to work with the equations.
So that kind of gets back to what we were talking about earlier. For a secant line and a tangent line, their derivatives are identical, right?
No. So the secant line is your average slope, right? Your tangent line is going to change as you move along the line. So your secant line, because it's always constant, is going to have a constant slope. The tangent line might have a non-constant slope. What your mean value theorem says is that at some point, that non-constant slope of your tangent line would have to be equal to constant slope of your secant line. That's all it's saying. It's not necessarily saying that their slopes are equal all the time. Answer all your questions?
Yes, sir.
All right. In that case, I'm going to go ahead and end the recording here. Thank you all for coming, and have a good